Okay, thank you. So shortly, I started more than 2 decades ago. I used to write C++ software, and we were a software vendor, so the software was run by banks across the world. And there I learned how to debug these exotic operating systems on the client side through email and phone, so without access to the systems. And today it's a bit kind of the same. I often don't have access to production systems, or oftentimes it's managed systems where you don't have all the tools available. So I learned to do that kind of with a set of tools that are available to everyone. First off, a disclaimer. So I will talk about solving issues. It doesn't mean that I'm a walking disaster that attracts those issues. I'm a kind of person that if I see a failure, I just have to know why it happened. So therefore, I do a lot of these investigations. I'm the first in line to look for the problems. I like this map. So Brendan Gregg, he has written books about systems performance, and he has a nice map about the system and different tools that are available to inspect different areas. So Brendan and some Oracle DBAs are source of my knowledge in most of cases. But let's start by basics. So the process file system, when we think about Unix, the thing that is taught is that in Unix everything is a file. Turns out that the processes as files were introduced only around 1984 in the 8th release of Unix, so pretty late. So what can we find inside the process file system? So there's a folder for each of the processes that are currently running. The one most useful file is there for each process is the CVD, so it's current working directory. It's a symbolic link. If you use read link, you can see which is the base folder where the process was started, and therefore you can kind of reason about why it's not finding certain files and where is it looking for them. The other important file there is environ. So this contains the process environment, but it's kind of C-style encoded strings with a binary 0. So what I typically do is I pipe this file through this translation utility, so I replace binary zeros with new lines, and then I get this nice printout. And since most cloud-native applications store secrets in the environment, then I can retrieve the secrets from there and then do some manual testing without going to secrets manager or asking somebody for permission. So another interesting folder there is the FD. So these are the file descriptors. File descriptors in Unix are numbers. And if you do a simple ls, you can find to which file name or some pseudo file this identifier is mapped. You can see that some of them are sockets, some of them are files, some of them are terminal input and output devices. So this is the list, and oftentimes when I want to discover which processes are using this file, I do something like this. So I look for all processes and list all their files, and then look for the specific file, and here I can find 4 processes which are using this Lua-snip log file. And so why this is general, so the most common use case for this folder is that in restoring deleted log files. So I have an application that I made, so it writes a log, and at some point it has written close to 10 gigabytes of logs. And there are 2 cases. Either somebody wants to free some disk space. He or she deletes the file, but this disk space is still used. It's not gone away. Or the other case is if you have some kind of badly set up log rotation, the newly created log file might be empty. System is kind of working, but the logs are not appearing anywhere. So for this, so the file is deleted. So why is the disk space not reclaimed? Well, the answer to that is that there is no such concept as to remove the file in the Unix. So the System call in Unix is called unlink. So what it does, it removes the file name from the directory. It actually keeps the file content on the disk until the last user of the file closes it. So in order to release the disk space, somebody has to kill the process. Therefore, there won't be any user of the file, and the disk space will be reclaimed. But by using the same principle, I can also restore log files. So for example, somebody deleted the logs, and I can go through the FD folder, and if I see this, so in my system it says deleted, so that it means that the file is gone. There's no such entry on the file system. And then instead of, so how to retrieve information out of it, I can just use this file descriptor as a normal file, so I can tail, kind of follow what is being written to the file, or I can save a snapshot of what is there, so by simply using cat. So some things like move or copy won't work, so it has to be cat because it has to physically read the file out and then store it somewhere else. So this is one of the use cases. But now, typically the problems are more complicated, and I have to understand what the application does at the runtime. And I have a tool which I use regardless of the programming language. And so now it's typically for Python programming, but I use it for applications written in Go, in Java, in C++. So this is strace. So what it does, it prints out the system calls that the application is making. And the best thing about it is that it doesn't require a root access, so unlike some other tools. And it also is important that if I ask some sysadmin to please run these commands as a root, he will be very skeptical. If I say run this as a regular user, it's quite okay. And probably now in the cloud environments, so the most attractive feature for me is that this can also be installed inside the pod without having root permissions. So it's as simple as unpacking a couple of files and then running that. So I have used it several times. So how does it work? So you can either attach to already running process, or you can launch some Unix commands under this tool. So there are a couple of parameters that I typically use. So number one is -s and some number. By default, it prints strings which are truncated to fit the screen, but I oftentimes need to have larger output to understand what's happening. So I increase this output. Then I like to use this T, which prints a very detailed timestamp. And then most of the time I forward it to some output file for later analysis. And this -f tells to if the process starts other processes or it starts new threads, then the strace should follow these newly created processes and threads. So what's the output? So this is output of one of the real applications. So even without knowing much about strace, you can probably spot that it's sending select distinct to somewhere. And a bit later, it's receiving something that contains request ID, so it's probably some field name. And so it prints a line for each system call, but so in reality, what it does, it actually prints each line in two parts. So before making a system call, it prints the entering part, so it prints the parameters that are passed into the system call, and typically then it waits at this point until the system call returns. So if the system call doesn't return, then it doesn't print it, it gets stuck there. But when it returns, so it prints this return value and probably some debug information about what's in the return. In a similar way, so again, another system call, it says that, so it's entering with these parameters and then it's receiving some output out. And for those who haven't done like low-level programming, so these are the typical system calls you expect to see. So something like epoll, poll, select, and things like that. So this is okay. It means that the process is waiting on multiple sockets. So that's what HTTP servers typically do. If you see write, send to, so it's writing data. And these typically do not cause any problems. So the accept system call, it means that it's accepting incoming connections. So yeah, sometimes it might block. It means it prints out the incoming parameters and doesn't print the return values. So in most of applications, it's kind of okay. So it's not a good style, but it's not completely bad as well. Now the next one is connect. So it connects to the some outside server. And if you see the entering part printed out without returning part, it means that the timeouts are not implemented, and this is really bad. So we actually do have connection timeouts in our application, but one time we had network issues. So we got a timeout error. We tried to report the error, but then the sentry kicked in and tried to report it to the centralized sentry. And turns out that the sentry themselves didn't implement the connection timeout, and the application just got stuck. And then it was hanging. So something like 6 months ago, they fixed the issue after I reported it. So it should be good now. The same for read and receive from. So it tries to receive some data. And if you see it hanging without the return value, again, it means that the timeout is not implemented. So it's really bad. And the other things you kind of expect to see is wait for. So it typically waits for some child process termination. And another interesting one is the futex. So it's fast user space mutexes. So it means the process is waiting on locks. I have a link to other system calls, but these are the common ones you expect to see. So very important feature is once you attach to some process, it will say something like this, that the process has 3 threads. And then first thing it does, it will print the current state of each of the thread. And then it will continue printing what the threads are doing. So here I see that the first thread, which ends with 07, is waiting on futex with some address, let's say address A. The next thread is again waiting on the futex with address B. And the third thread, so it was sleeping and then it continues to get PID and write something on the screen. But the 2 threads above are stuck. So since they are waiting on a different locks, it indicates that there's a deadlock in the process. So and this is, I have actually seen it a couple of times. So pay attention to what it prints first. And a bit story time. So we received complaints that the system is slow. So we have some background tasks which were not doing their job on time. So the data was not being updated. So we connected to the server, looked at the CPU load. So it was quite high, but it's normal for that specific application. But what was interesting, it also had a high I/O load. So I'm a bit old school. I use an application called Nmon. If you don't have it, you can also use the standard I/O stat with -x. So what does -x? It prints out the utilization percentage of the I/O device. So you don't have to know the maximum and the current value. It just gives like, is it 80% utilized or so? In this case, it was 80% utilized. So we found out the PIDs of background tasks and run strace on them. So what the process was doing, it was basically checking a bunch of files. So stat is retrieving the file sizes and permissions of a file. And what was happening is that we had a custom Django file field, and it was looking for a file in several folders. So it had like kind of this active folder and then the backup folder and then like kind of called backup folder. And it was checking in which of these the file was residing. And by some accidental change, this background task was loading more objects than it usually did. And so in most cases, what people would do would go and start implementing some caches, add Redis to kind of speed it up. But what was interesting was the I/O load, so high I/O load. So my experience tells it shouldn't be that high. And it's a bit complicated topic. The short version is that the vendors and the cloud providers, they typically give you throughput. And the way to achieve throughput is either to do a lot of operations really fast, or you do slow operations with large data sizes, and they typically do the latter. And the numbers kind of look good, but the thing is that Unix file systems work with 4K blocks. Databases typically work with 8K blocks. And whenever you print something in your container, like a log entry to the screen, it actually gets stored by the container runtime to the disk. So it means it will do a small 4K write. Similar for the database, every time you do a small update, it typically like writes 1 or 2 blocks, so it doesn't write like huge amount of data. And when I assess performance, I typically look at the write performance because it's more reliable to measure it, so it doesn't, the caches do not affect it, and it's kind of easier to measure. So long story short, we did the measurement of the newly bought enterprise servers with enterprise Sun device. So if run with small block sizes, it was performing only 27 megabytes per second. Of course, it can do more if you do it in parallel. But for comparison, the old Hetzner machine, which was something like 3 years old at the time, and we migrated away from it, it was doing more than 10 times of that. So instead of fixing the code, we talked with the provider. Eventually, they managed to double the speed, but it was still quite low. But it is what it is. At least we didn't do any like useless optimizations on the code side, so this hardware was to blame. Then about networks, so oftentimes we integrate with different companies, and since I'm in finance, then there's strict like security rules. The typical is that our company opens some route through the firewall, and same does the other side, and then they do it and they say, okay, now it's done. We as an application developers try to run some tests and it doesn't work. And then the admins on both ends say, oh, well, we did everything that you asked for us. It should be working. It's your problem. And then if you try to debug it as a developer, what internet says, use ping, use traceroute, but it doesn't work in modern environments because most of the time ICMP and UDP protocols are blocked if you have a reasonably good network admin. So what to do, there's a tool called TCP traceroute. So it acts like a traceroute, but it uses TCP packages. So it always kind of works. And it gives you output kind of like this. So the path where the packet was going until it reached the destination host and port. And then you show this to the admins and they say, oh yeah, well, why the packets are going out through this way instead of this router where we opened the ports. And so they fix some routing information, and so eventually everything works. So this is a nice tool. And another story time. So we started to do projects using Kafka. So we had a consumer which reads messages, then enriches them, and produces new events out of it. And we did some kind of light stress test. And a single consumer producer was doing only like 20 events per second, which is kind of too low. So I got some time to look into this problem. So first off, turning on the logs on the librd Kafka. And it really said that, okay, so the message took 43 milliseconds to be sent. Okay. So I actually managed to install TCP trace as well on the Kubernetes container or pod. So I did the TCP trace route. Turns out the network is pretty fast, so it's a single millisecond. It shouldn't take 40 milliseconds to do something. After that, I installed strace because I had suspicion maybe there's some locking issues with multiple processes, and Python is not like exactly great at multi-threading. So what it revealed is that it really took something like 47 milliseconds inside the poll. So if you see the poll call entered, and then after a while it exited. And yeah, so it's really, at this point, there's no further way how to investigate this. It's just something you have to know. So Whenever you see limitation of 40 milliseconds or around 25 transactions per second, it means that it's this TCP no delay. I have recently seen quite some articles about people discovering this again. And people assign this to the Nagel algorithm. But in reality, it's interaction between Nagel's algorithm and the delayed ACK. And out of these two, I think the delayed ACK is the wrong one. But somehow people fix this by disabling the Nagel's algorithm. So there are some articles, and yeah, while doing the presentation, I actually found the exact line in the Linux kernel code where this 40 millisecond timeout is set in the code. So that's it. So how to fix it? Yeah, there's basically a Kafka, non-default Kafka parameter that you have to set. We have ticket open for 2 years. They still haven't fixed it. So they still haven't changed the default value. And another story time. So this time about timeouts. So there was a Python server which was doing like calculations about calculating risks. It had Scala HTTP client all running on Kubernetes. And the way it was implemented is that this endpoint receives basically a CSV file. It runs calculation on all rows and returns a result. So depending on the number of rows, it took more or less time, which is not the best solution, but it is what it is. And the thing is, of course, everything worked on the developer's machine, but once it's in Kubernetes, it stopped working. So small requests, it was taking a minute, maybe 2 minutes, 3, 4 minutes, and then it was 2 hours and an error. So obviously we it works on developer machines. So we connected to Kubernetes machine, Kubernetes pod, installed curl on it, and surprisingly everything worked with curl. So the question was, what does the curl do differently? So it turns out it's setting these 3 additional values. So for TCP keep alive, so it's setting 60 seconds interval. Why does it do so? It turns out that the defaults in Linux are really bad. So what it means is that Linux will send the first TCP keep alive packet only after 2 hours of being idle, and it will do it for 9 times with a 75-second interval before giving up. And how is it related to Scala and how is it related to Python? So it turns out Python is now better, so it doesn't set these keep alives. But what it does, it says TCP no delay, unlike Kafka. So 1+ for Python. So this is a problem in Python as well. So what is really happening is that some firewall or gateway in between drops connections after 5 minutes of inactivity. Client is not aware of it. Server is not aware of it. Server continues to work, tries to deliver response back. Not happening. That's not happening. And then client starts sending keep alive after 2 hours, and then after a few more minutes, it realizes, oh, the connection is gone. If you think, 2 more minutes. So if you think this is, okay, that was a stupid case, you shouldn't use HTTP for this. Actually, all our Python applications have long-lived connections. Those are the database connections. Lucky for us, there are some parameters in the Postgres library which allow to set you a better keep alive interval and idle time as the Linux defaults. So you should do that. The way I solved it for Scala, and if I don't have access to modify the source code, this is the preferred way. So there's a library, you can load it, and then from that on, all connections that will be created from this process will have the keep alive set and fixed automatically. And it all works fine until your Kubernetes team decides to install something like linkerd proxy, so service mesh, which intercepts your nicely connection, and so the TCP keep alive works between your application and linkerd proxy, but it loses it between the linkerd proxy and the database. And yeah, so that's it. So kind of summary, look into a process file system. It contains a lot of nice stuff. Learn nest trace, TCP trace route, set timeouts for everything. so just save yourself trouble. Remember about these magic 40 millisecond, 25 transactions per second, magic numbers. Yeah, set a better keep alives, and also measure your disk I/O, because surprise, surprise, typically all the cloud providers have pretty bad disk I/O, and you might go into optimizing your application, implementing different solutions instead of getting a good database instance with a good database disk. So that's it. Thank you.
Thank you very, thank you very much, Aivars. That was really interesting. I'm afraid we don't have any time for questions, but I'm sure you'll be happy to discuss any or all of this in the corridors.